On Tuesday I woke up, and I think hopefully we've alluded to this in lecture a little bit. I know I showed one of my sections, this demonstration. We might get to it later in the class, but so maybe some of you have heard a little bit about like why the sky is blue and why sunsets are red, and it has to do with things in the atmosphere scattering light at different wavelengths. And so one of the ideas was that if you get a lot of stuff in the atmosphere, it's going to scatter more blue light and leave the red light so the sun looks red. And I know I did a demonstration in my section, and I said, you know, you can't just randomly add stuff to the atmosphere to do this. You have to find another way. But it turns out that if you set half the state of California on fire, you can add a lot of stuff to the atmosphere. And so I woke up Tuesday morning at like 11 o'clock, and I went outside, and it was like it was sunset. The sun was bright red in the middle of the day because of all this smoke from these fires. So I don't know, stuff that's happening all the time is affecting stuff that we do as astronomers. Certainly the star parties were a little bit more low quality this week because of all the gunk in the atmosphere messing up some of the sharpness of the images. And so I thought that was interesting. You guys don't have to if you don't want to. All right, we've got about another minute. No one really has any jokes? No? Okay. Okay, that clock says 3:10, so I'm going to start. We'll start in easy. I am Nicholas. I'm Alex's head GSI. As he said on Wednesday, Alex is in England right now. He's accepting the Gruber Cosmology Prize, which is, I guess, a prestigious award that's given out to groups that have done a significant contribution to cosmology, the study of the origins of the universe. And so an old version of the group that Alex currently works with has been awarded this prize, and so he's partying it up in England, getting awards and stuff, and I'm here to give his lectures. So today's lecture, as you can see, the title is Black Body Radiation. Black body is a term I'll discuss in a little bit. It's maybe not the most important thing. I'd say the most important thing that we're going to talk about today is sort of the colors of stars, is how we're going to start getting into it. And it turns out that if you think about why stars are different colors, there's actually a relationship that you can define pretty well between a star's color and its temperature. And so that's a big thing that I want you guys to take away from today's lecture. The other cool thing about this, which I think is even cooler than the fact that this relationship exists for stars, is that actually you can use that same relationship and apply it to almost anything in the universe. And so we can take this relationship I'm going to show you that tells you how stars of certain temperatures will have certain colors, and in a similar way you can apply it to your own body or to objects you encounter on Earth or planets or anything else. So we're going to discuss things that can actually be applied to things all over the universe that maybe don't seem very similar. I hope none of you think that you're actually that similar in structure or in physics to a star, although there are some fundamental laws that connect them all. So that's sort of going to be the theme for today. Another reminder for today. Hello, please work. There we go. That's not the big reminder. Is that the first homework assignment is due. It's due at 5:15 this afternoon. If you go to the basement of Campbell Hall, room 11, which is basically the only room that exists in the basement of Campbell Hall. As soon as you get down there, you'll see the homework boxes. They'll be labeled with your GSI's name, your section number, when your section meets, so you shouldn't have any trouble finding the right slot to put your homework in. Submit it there, please. We've gone over these announcements earlier this week, but just remember to put your name, your SID number, your GSI's name, and your section number on your homework. Staple it if it's multiple pages. We have this official cheating policy that I hope you guys have read by now. And again, just the bottom line is we want you guys to be working together. It's good to collaborate, but you in the end have to write your own original homework solutions. And so the work that you should be submitting, your written work, needs to be in your own words, and the graders will be looking out for that. And the last thing is we're not going to accept late homework at all. This course policy is that you turn in 9 homework assignments, and at the end of the year, we choose your 7 highest grades. And so if there's an occasion where you turn it in late, we'll give you a 0 for that week, but assuming you don't turn it in late every week, that 0 will end up being dropped when we calculate your final grade. So you sort of have a 2-assignment buffer, and that's why we're not taking any exceptions if you turn in late work. So I think that's fair. And finally, go Bears! All right. First, I just want to review a couple things that Alex said on Wednesday, or the basic gist of his lecture on Wednesday. And that was essentially that we talked about some of the phenomena that happen when you take starlight and spread it out so you can see it at its different wavelengths. And so in particular, what you see here is that if you were to put starlight through a prism, it would be spread into these wavelengths. And when we talk about stars, we see these gaps in this spectrum where there are absorption patterns from atoms. And we talked about how the atoms work to do that last time. And so another picture that you might have seen, a picture that's sort of common that we'll see over and over again in this course, is this notion of a spectrum. So since it's a basic idea, let me remind you what that is. When we say we take a spectrum of an object, it means that we sorted out the light so that we can see all the different wavelengths. And so in a plot here, you can see that on the horizontal axis we have the wavelengths, so the different wavelengths, and then on the vertical axis what we're plotting is the brightness at each wavelength. So this is a plot of brightness versus wavelength. And so again, Alex was talking mostly on Wednesday about what phenomena give you these lines that you see biting into the normal spectrum of the star. Today, I'm going to spend most of the time talking about the main pattern of the spectrum, which is this broad hump here. And so we're going to talk about that and what you can do with it and how it's related to, for instance, the color of different stars. Before we get into that, though, I want to introduce another topic that astronomers use all the time. It's a very important topic, and it's called the Doppler effect. It's something that, as the slide says, you can use to determine the radial velocity of a star. So that means you can use it to figure out how fast an object is moving with respect to us. And by radial velocity, we specifically mean an object's speed coming towards us or going away from us. So in cases where we'd be interested in knowing how fast an object is approaching us or how fast an object is receding from us, the Doppler effect is something that allows us to precisely calculate that. And to understand the Doppler effect, before we talk about an object that is moving, it's good to start with an object that isn't moving at all. So up here is a picture of a light source that is emitting light waves, and it isn't moving anywhere. And so as this thing tries to depict, if you put a marker, one of these circles, at each crest of the light that's being emitted from this source, you can see that as the source emits light and as light travels away from it at, of course, the speed of light, that these crests sort of move outwards. And so our markers form a pattern of concentric circles where as the light moves outwards, the circles expand from the source of the light. If thinking about light in this term is a little difficult, another analogy that I like to use with water waves is if you think about someone in a rowboat in the middle of a pond and you think about them dropping pebbles into the pond at a very regular rate, maybe one pebble every second, then every second when the pebble hits the water, it's going to create ripples, and those ripples are going to travel away from where the pebbles were dropped. So it's the same idea with light. And so, again, we get this nice pattern of concentric circles when the source isn't moving at all whatsoever and when we're not moving with respect to the source. But if the source starts moving, the pattern becomes a little bit different. And so it's the same idea. Something's emitting light. Light has a single frequency when it's being emitted. Or you can think of someone dropping pebbles into water at a specific rate. But at this case, at the same time this is happening, the source is moving. And so whereas these would have been concentric circles in the last slide, now the pattern has changed because as the light source emits light or as the person drops pebbles into the water, they move. And in this case, the source is moving from right to left. So we started there, then went there, then went there, then went there. And each of these circles is centered at the origin, exactly where the source was when it emitted the light. And so as you can see, the pattern that you get is different when you're standing in front of the source versus when you're standing behind the source. And you see that in front of the source, the wavelengths get scrunched together. And when they get scrunched together, it means that you're observing a shorter wavelength than the wavelength you would have observed if the source wasn't moving at all. And so we call this a blue shift, and we do that, whoa, no good. We do that because even though this doesn't always happen in the visible spectrum, if we think about the visible spectrum of light, we know that blue light has the shortest wavelengths in the visible spectrum, whereas red light has longer wavelengths. So when we're standing in front of an object and we see the wavelength getting shorter, we know that we call that a blue shift, even if it's not actually happening in the visual spectrum. If it's happening with radio waves or with ultraviolet light or X-rays or anything like that, we still use the vocabulary blue shift for waves that are getting scrunched together when an object is moving towards you. On the other hand, if you're behind the source, so you see the source moving away from you, you see the opposite effect. You see these wavelengths, the location of these crests, get spread out. And so because we're getting longer wavelengths, if we're thinking about the visual spectrum, that's the red end of the visual spectrum, we refer to this phenomenon as a red shift. So again, you get a red shift if the source is moving away from you, and you get a blue shift if the source is moving towards you. And the other thing to note about this, and this is true only for light, which is fortunately what we're going to be dealing with in this course, is that it doesn't really matter whether the source is moving or you are moving. What matters is the relative motion. And so if I'm standing still and a source is moving towards me, I'm going to see a blue shift. If the source is standing still and I'm moving towards it, I'm still going to see a blue shift, and the opposite effect if I'm moving away from the source or the source is moving away from me. Go. And so in astronomy, one of the ways that we measure this is we saw in Wednesday's lecture that we have these absorption features, lines in the patterns of stars that tell them what they're made of. So in this case, if we're looking at an object and we see its spectrum, and that object is also moving towards us or moving away from us, we will see the spectrum shifted. And so here, for instance, is the H alpha line of hydrogen, or maybe you guys who have done the homework are much more familiar with this 4861 angstrom H beta line. And so if the source was not moving at all, we wouldn't see any shift. We would measure H beta, for instance, to be exactly at the 4861 angstroms that we expect. However, if the source is moving away from us, or if we're moving away from the source, then we see everything in this spectrum, oh goodness, everything in the spectrum gets shifted to longer wavelengths. So we call that a redshift, and it's just like drawn here, where you see everything shifted over. On the other hand, if we were moving towards the source, or the source was moving towards us, we'd have things shifted towards shorter wavelengths, and that would be a blue shift. So it's nice to know just generally what direction a source is moving with respect to us. It's even better to know if we can actually calculate the exact speed at which this motion is happening. And it so happens that we can. We have a formula for calculating the speed v of an object based on what we measure its features at. And so in this formula, we have lambda. Lambda is what we measure. So it's the wavelength that we actually measure when we're looking at a source. Lambda naught is what we expect to measure. So if we were to go back here, lambda naught would be this 4861 angstroms that we know hydrogen has when there's no motion. And if there were a redshift, we'd actually be measuring a slightly different value of lambda. And this shift between the value we measure and the value we expect is this delta lambda here. And so the formula for Doppler velocities is to have delta lambda over the wavelength we expect, and that's equal to the speed at which the object is moving relative to us over the speed of light. It's important to note that this formula is only valid when things are moving much slower than the speed of light, which is basically true almost all the time. When things get relativistic, when they start moving close to the speed of light, we have to use a different formula. I think we'll bring that up for one example later in the course, but for now this formula is all you need to know. So the example down here is, again, suppose that we expect to see the H alpha line, which is at 65, 63 angstroms. Right here is where we expect it. And suppose that instead over here we measure it at 65, 65 angstroms. So then to figure out the velocity of the source that was calculating that, we would subtract the wavelength we measure from the wavelength we expect. We get an answer of two wavelengths. And also right now we should already be thinking, is the source moving towards us or is it moving away from us? And so in this case, have we measured something longer or shorter than what we expected to measure? Longer, good. And because we've measured a longer wavelength than we expect, what does that tell us about the direction of the source? Which way is it going? Good. It's receding. It's moving away from us. And so in this case, when we plug in the math, this is a difference of 2 angstroms. We divide it by the original 65, 63. So you notice that this is a relatively very small shift. The speed we get is not going to be comparable to the speed of light. So when we plug in the numbers, we get 3 times 10 to the negative 4. So that's V over C. To figure out what speed that is in units we like, we would then multiply that ratio by the speed of light. And so when we multiply 3 times 10 to the negative 4 by the speed of light, we get this number, 90 kilometers per second. And just to give you a sense about how fast that is, the Earth moves around the Sun at about 30 kilometers a second. So this is about 3 times the Earth's orbital distance around the Sun. So before I go on, are there any questions about that? About any of this Doppler shift stuff? All right. I think a funny example of the Doppler shift is you may have seen this bumper sticker before. If this bumper sticker is blue, you're driving too fast. But it's actually a red one, so hopefully you see it as red. And if you did the calculation, you'd actually find that for this red bumper sticker to be Doppler shifted to appear blue, you'd have to be moving at like half the speed of light or something. So realistically, you'd see this, and then an instant later, you'd crash into the car behind you, and it just wouldn't be any good. But nonetheless. A more realistic use of the Doppler shift, one that's sort of a hot topic in astronomy right now, is astronomers have been using the Doppler shift for about the last 15 years to detect planets that are orbiting other stars. And so right now, I don't know if you knew this, we know of about 200 planets that are orbiting stars other than the Sun, so-called extrasolar planets. And the way we found by far the most of these planets is not by actually taking a picture of them. We've taken a picture between 0 or 2 pictures of extrasolar planets, depending on who you listen to. but we find them mostly by looking at their stars and seeing their stars wobble back and forth in space. And so we'll talk about this a little later, but the idea is when you have a large planet like Jupiter orbiting a star, that planet's gravity is going to tug on the star a little bit. So even though the main motion is the planet moving around the star also moves back a little bit in response to the planet. And so stars that have large planets orbiting them move in rather small circles, around and around. And our telescopes actually aren't good enough that we can see the stars move back and forth in space. That's not a way we detect them. But the Doppler technique does allow us to detect them moving towards us and away from us. And so if we take the spectrum of a star, again, astronomers such as Jeff Marcy here at the University of California have been doing this for about 15 years, and we see that periodically we observe a red shift and then a blue shift and then a red shift and then a blue shift, and we observe via these Doppler shifts the star moving back and forth periodically over time. We infer that there must be a planet orbiting that star. And so we've done this for many, many stars, and we found about 200 planets using this technique. And 20 years ago, no one knew that there were actually planets around other stars, but thanks to the Doppler effect, now we do. All right, questions there? Okay. What time is it? All right. So let's get back to actually looking at the spectrum of stars. And like I said, on Wednesday, Alex was talking about these absorption features. Today, I'm going to talk more about this broad pattern where the star is brightest at a particular wavelength, and then dimmer at wavelengths short of it, and dimmer at wavelengths long of it. And one of the basic ways we can ask this question, sort of an even rougher depiction than this graph depicts, is simply asking what color are stars when we look at them and why are they that color? And so hopefully if you've looked at the clear night sky, not the night sky we've had this week, which has been pretty terrible, but a clear night, you'll never get a night this clear from Berkeley, but pretend that you do, you'll see that different stars actually have different colors. And so here's a picture of the night sky. Does anyone recognize the constellation in this picture? No? If I circle it down here, what constellation is this right here? Orion. Very good. So this is the constellation Orion. If you can't pick it out, here's Orion's belt. Here's the sword. And so I want to point out in the constellation Orion, you can see this very clearly if you look at it in the real night sky. Orion's up sort of in the early morning at this time of the year. If you look at the top left part of Orion, you'll see this big red star called Betelgeuse. And it's not the cartoon character with the striped shirt. It's a different spelling. But it's still called Betelgeuse, and hopefully in this picture you can see that Betelgeuse is quite red. In the sky you'd also see that. Whereas if you go to the bottom right of Orion, you see this blue star called Rigel, and it's another very bright star, but it should look like quite a different color from Betelgeuse. Sometimes if just looking at these stars as single points isn't clear enough to get the color distinction, another thing you can do, or you can see someone else having taken a picture of, is leave your camera shutter open for a while and let the stars track across the sky so they leave these trails as the Earth rotates. And then hopefully in this image you can see that some of these star trails are red from very red stars and others are more blue from very blue stars. Does everyone see that? All right. And so the question again comes down to why are some stars red and why are some stars blue? And it really boils down to their temperature. And so the basic relationship between red stars and blue stars, the qualitative thing we can say about them is this, that hot stars are the stars that are blue, and cold stars are the stars that are red. And the reason that stars glow at different colors based on their different temperatures has to do with what it actually means to have a temperature. What do we mean physically by the notion of having a temperature? And so when we describe the temperature of an object, what we're actually describing is the motion of tiny individual particles, atomic nuclei and electrons and molecules in these bodies. And so when I say that an object has a high temperature or an object has a low temperature, I'm referring to the fact that inside each of these objects there is random motion between the atoms and the nuclei and the electrons. And Alex does this motion a lot better than I do. He has a lot of practice. But Alex likes to say that all these objects have random jiggly motions like this. And it's quite true. And so the relationship between temperature and these random motions inside an object is that as an object gets hotter and hotter, as you increase the temperature, that is in effect increasing the speed of these random motions. So a cold object would be kind of slugging along, maybe Rocky when he's in like the 14th round of some title fight. And a fast object is more like round one when it's just punching all over the place. And so I said a fast object, so obviously this is fast. A hot object has high velocity random jiggly motions, and that contributes to why it turns blue. We haven't put it all together yet, you and me. And so the last thing is, why do these things emit light in the first place? Why does having a high temperature and really speedy random motions mean that you emit blue light instead of red light? And so if you think about individual photons, you remember hopefully a relationship where the shorter a wavelength of a photon, or the higher the frequency, the more energy that photon has. So because blue light has a shorter wavelength than red light, a photon of blue light is going to have more energy than a photon of red light. And so hopefully, the other thing that we want to know, I should say, is that when you have charged particles, like electrons or like atomic nuclei accelerating around, that is one way to emit light. And so because we have all these random motions with these charged particles inside us and inside stars, because they're changing direction and accelerating and all of that stuff, they are constantly emitting light. And hopefully it makes sense that as they move and accelerate faster, they're going to emit higher energy light. And that's why when you get a high temperature and you get fast random motions, you get blue light, which is higher energy, whereas if you decrease the temperature more, you get redder, lower energy light. And we'll see that you can decrease the temperature further and get yourself all the way out of the visible spectrum altogether. And then the last thing is that, okay, we know cold stars are red, we know hot stars are blue, but medium temperature stars appear white. And it's not because white is, a color in the rainbow. There's no Roy G. W. Biv. But actually, when you have a cold star, it's emitting mostly red light. By the time it's hot, it's emitting mostly blue. But for these medium temperature stars, they sort of represent all the colors approximately equally. And so a star like the sun is emitting a significant amount of blue light and green light and yellow light and red light. And as we know from Isaac Newton's experiment, when you combine all those different colors of light, you get white light. So that's why the sun glows white hot, and why most of the medium temperature stars you see in the night sky don't appear really that colored, but appear white in the end. So you might be a little bit nervous about what I'm saying, because this whole point that I've been making is that blue things are hot and red things are cold. But that kind of goes counter against stuff that we encounter every day. I mean, we like to think, as this slide says, about cold ice or a refreshing cold blue drink of water, or hot coals, or the hot stove that you don't want to touch because it's going to burn you. So, I mean, it's worth asking, what's going on here if the stars have the opposite relationship from maybe what you've learned on Earth? Alex likes to take pictures when he goes to hotel rooms. Who knows what he's going to have when he comes back from England? But something that he took, okay, so this is a blue iceberg that you can see is quite blue and cold. And these are hot coals that you can see are red and hot. And some pictures Alex has taken, here we go, from a hotel room, are just sort of this standard idea where it's been ingrained in all of us that red is hot and blue is cold, when in fact that's completely wrong. But nonetheless, this heater he found in a hotel room has shown this, and he got angry enough to take a close-up photograph to show that, no, they did it wrong. Even on the temperature dial, it's wrong. Maybe some of you guys in your shower, it's just wrong all the time. So we should ask ourselves, is there a reason this convention exists? I mean, we know that ice is cold and blue, and yet the hottest stars are hot and blue. And what's going on with that? And so what we want to think about is, what we really should ask, where am I? Sorry. Is the color that we see in ice and the color that we see in hot coals the same as the color that we see coming from stars? Or is there a different phenomena that we need to think about when we talk about ice and when we talk about coals? So I'd suggest, why don't we start with the red hot coals first? And so when you see red hot coals, it turns out that they are red, glowing from about the same mechanism that the stars are. Just like the stars are very hot and so have these intense random motions inside them and therefore glow in the visible light, the coals do something similar too. It turns out that hot coals aren't quite as hot as even the coolest stars. They're less hot than stars. So even though they're hot, they're not so hot that they emit most of their light in red. They actually emit most of their light in the infrared. And hopefully, if you've stood near hot coals, you notice that you can feel the heat emanating off of these coals, and that mostly has to do with the infrared radiation these are emitting. Nonetheless, coals are hot enough that some of their spectrum spills over a little bit into the red part of the spectrum, and so you do see some red light from hot coals, and therefore they appear red, in a similar way to why red stars appear red. Ice, on the other hand, does not appear blue because it is very, very hot. Rest assured, cold ice is not hotter than the hottest stars. We're not doing some sort of weird conundrum there. And so the reason that ice appears blue is not because it's glowing blue, it's because light is reflecting off the light off the ice, and blue light reflects better than other colors of light. In a similar example, I see a couple students out there who are being vastly treacherous and wearing red t-shirts out there. I am wearing a blue California Bears t-shirt. And so maybe based on all this gibberish I've been talking about stars, you would argue that my blue t-shirt is hotter than the red t-shirt. And I would say from a pop culture standpoint, it's absolutely true. But from a physical standpoint, they're not. My t-shirt is almost definitely about the same temperature as some red t-shirt in the audience, and yet they appear different colors. And that has more to do with the dyes inside the t-shirt. My t-shirt has a dye that absorbs a lot of colors, but doesn't absorb blue very well, and therefore it appears blue. The traders out there have chosen to wear t-shirts that absorb blue very well, and yet the red does not absorb well, and it marks them as traders very clearly like that. So if we go back, I can give more examples. Again, this orange basketball might be slightly warmer than the blue ice, but it is not orange because it is glowing orange hot. I'll throw it to you. You can see that it's not glowing orange hot. It's not burning your hands, is it? No. So it's glowing because it absorbs most light, but it reflects orange light rather well. So we're seeing it orange in reflected light, not the light that it's intrinsically glowing. But as we've said, stars, on the other hand, are different. Stars aren't reflecting light from other bodies. They are actually the colors they are because they are so hot that they are glowing in those particular colors. And so when you see starlight from so far away that you see it, you're seeing a very bright, glowing, hot object. So let me pause and ask if there are any questions about that. Yeah, in front. I haven't gotten into the details of why the iceberg reflects blue light better and other colors of light worse, and I don't think I'm going to right now. Alex mentioned this. There was a similar question earlier this week, and how colors reflect and get absorbed and then how we perceive them in our eyes is a rather complicated phenomenon. So I'm not going to answer that question because I don't feel qualified to, but it's a good thing to ask. Physicists would certainly like to know that. I'm sure some do also. There's a question out there. That's a good question. The question was, when you burn a candle or you look at a flame and there's a blue center, is that because that's the hottest part? And again, I'm going to plead partial ignorance. I think that has more to do with the different chemicals that are being ignited inside the flame, and that chemicals will sometimes burn at different colors. But I'm not so sure of that it can't be true. We'll do a thought experiment in a second where we heat up an iron rod, and we talk about how the color changes in this iron rod that we, in our minds, heat up, and maybe that'll help clarify that. But I'm not sure how it works exactly with flame. All right, I'll take one more question way there in the back. That's a really good question. And so the question was, are the stars blue because they're moving towards us or because they're hotter? And the answer is, for the most part, it's because they're hotter. Really, stars don't move towards us for the most part at speeds that are fast enough to actually see a change in color when we do the Doppler shift, but they are blue because of their temperature. And so in theory, if you rocketed a star towards us at something close to the speed of light, you might see such a dramatic blue shift that the whole star does appear blue. But usually the phenomenon is not nearly that dramatic that you would actually see it change color. But that's a really good question. All right, I'm actually going to move on just to make sure that we stay on target. And so to get a little more precise about this, if we go ahead and plot what the spectrum of a star looks like, how the brightness gets distributed over the different wavelengths, you get a shape that looks something like this. And here's the title of the lecture, Black Bodies. Again, this is a technical term I'll describe in just a couple of seconds. I just want to point out that this shape that you see right here, this so-called black body spectrum, is basically the same shape that you saw a few slides ago, where there was a hump on top and a hump with absorption lines on the bottom. This is essentially the same hump, it's just been scrunched up a little bit, but it's the same general idea. And so the notion is that any object with a temperature radiates light, and it radiates most of its light at a specific wavelength. And if you go to shorter wavelengths, it radiates less light at those wavelengths, and if you go to longer wavelengths, it emits less light at those wavelengths. And so black body is a technical term for what we call a perfect emitter, something that has no flaws in the way that it emits light. And no object in the universe, except maybe a black hole, is actually a black body. Stars are not black bodies. Our bodies are not black bodies. But when it comes down to it, most objects that are solid and opaque are close enough to being black bodies that we can talk about them in the same way. We can use this shape of brightness versus wavelength to more or less describe any solid opaque object in the universe. So when we talk about black bodies, know that the object I talk about, stars and our bodies, aren't perfect black bodies in that sense, but they're close enough that we talk about them the same way. If you want to use the more general term thermal emitter, something that's glowing at some wavelength because it has a temperature, that's a general term that's sort of maybe better and all-encompassing. And so, again, this trend that we've been talking about is, I've said, hotter things are blue, colder things are red. You can see that in this graph of things with different temperatures, so these are all sort of stellar temperatures, 6,000 Kelvin, for instance, is close to the surface temperature of the sun. You can see that as the objects get hotter, they emit their most radiation, they have their peak wavelength at a bluer color. And so this cooler object, about the temperature of the sun, emits somewhere in the yellow-green region of the spectrum. Like I said, near the top of this hump, you can see blue and green and yellow, and all of the colors there. All of the colors there. So this is why it would appear white, because all of these colors are being fairly well represented. And as you get cooler, its peak is closer to the red part of the spectrum, and it appears redder. One thing to note about these temperature scales, so if you go back and look at these temperatures, they have a K after them. K stands for Kelvin. And we're not going to harp too much on different temperature scales or how to convert them, but it's good to know that scientists prefer to use this Kelvin temperature scale, which has the advantage of being an absolute temperature scale. Kelvin temperatures are nice because there is no such thing as a negative temperature in Kelvin. And if you think back to why physically objects have temperature, that kind of makes sense. Because you can think about an object with a certain temperature, that, here we go again, has random motions in its particles, and you know that as you cool the object down, what happens to the motions? They slow down. Rocky Balboa starts getting tired and he slows down. And eventually, if you keep cooling it down and keep cooling it down, in theory, and you have to ignore quantum physics to actually get this right, but pretend there's no quantum physics, eventually as you suck all the energy out of it and it gets down to zero temperature, you would think that these random motions would slow down and stop entirely. And so ignoring quantum physics, which has some different things to say about this, when you get to 0 Kelvin, that in theory corresponds to no random motion whatsoever. And so that way it's a fairly intuitive scale, and it's the one that scientists like to use. A quick conversion from Celsius to Kelvin is if you have a Celsius temperature, just add 273 to it, and you get Kelvin. When we're dealing with large temperatures in the 1,000, that 200 sum actually doesn't make that big a difference. So a star that is a few thousand Kelvin is also going to be a few thousand degrees centigrade, by far hotter than most of the stuff we experience here on Earth. So that's just a brief note on temperature scales. And I just want to demonstrate here another thing that shows, again, how if you adjust the temperature of an object, you can see how its spectrum changes and how the peak appears at a different wavelength. So here's a star that I've set up to be about the temperature of the sun. 5,800 Kelvin is more or less the surface temperature of the sun. You can see it's whitish, like the sun is. And here's a graph of how bright it is at all of these different wavelengths. And so if I change the temperature to make it warmer, you can see that this is moving, so the peak wavelength is sliding over into the blue, and maybe as I move it further up, the star actually begins to appear somewhat blue. Everyone can see that. And as I cool it down, it moves back, and eventually as it gets colder than the sun, it starts appearing very red, and it's hard to make out the peak here, but the peak over here is more in the red wavelengths. And so again, this is just bringing it home that hot objects appear more blue, or at least emit at shorter wavelengths, and cold objects emit at longer wavelengths. Back here. All right. And so I said we were going to talk about a hot iron rod. So a thought experiment you can do, if you have access to a blacksmith's facilities, I suppose you could do this experiment in real life, but we'll just keep it as a thought experiment, is if you take an iron rod and you start heating it up, and you get really intense heat going through the rod, it's going to start glowing. And what color is it going to glow first? Red. Good. It's going to start glowing red like these coals. And then just like a star, as you heat it up more and more and more, it's going to go from red, and as it starts creeping its peak into the yellow and into the orange and into those parts of the spectrum, it's going to start glowing kind of white because more and more colors are getting represented. And at some point when, like the sun, it's in the middle of the spectrum, its peak, it's going to appear white, so you'll have a white, hot iron rod. I'm not sure if there's a heavy metal band named after that, but it sounds like there should be. And if you heat it up even more, then it might even become blue hot. And I don't know at what temperature the iron starts melting and ruining your blacksmith equipment, but at some point you could imagine something as it gets hotter and hotter and hotter going from red to white, then to blue. How patriotic. All right. And so finally, again, like the Doppler shift, it's nice to know the qualitative relationship, but there's also a quantitative way we can describe the relationship between an object's temperature and the wavelength it emits most of its light. And so this is the same version of these images you've seen before. And again, we get to this mathematical relationship, which is called Wien's law, named after a German scientist. And Wien's law is rather simple. It simply says that the peak wavelength, so here would be the peak wavelength for object 4, for object 3, it peaks around 5,000 angstroms, object 2, etc., times the object's temperature in Kelvin equals a constant. If you've taken this class, if you're getting comfortable, you should know that you should feel good when things equal constants. That's a good thing. And so the product of the peak wavelength and the temperature equal a constant. The constant is about 2.9 times 10 to the 7 angstrom Kelvin. And so you can figure out, here's a list of peak wavelengths and the temperatures that correspond to them. And so these spectra are like the applet I just showed you or other thing you've seen before. So it might be worth asking, okay, I know stars are sort of thousands of kelvins hot, and I know their peak wavelengths are in the visible. Well, what about me? I am a solid opaque object. Hopefully you guys can't see through me, can you? No, good. So I'm a solid opaque object. I have a temperature, at least I'm pretty sure that I do, and therefore I should be radiating some kind of light. I hope you guys don't see me glowing up here either. I just look kind of normal, right? Yeah, all right, I look normal enough, but I've got to be glowing somewhere. I have a temperature. And so let's use Wien's law to calculate, based on my body temperature, where my peak wavelength should actually be. And so using the Kelvin scale, we know that 0 Celsius, the freezing temperature of water, is about 273 Kelvin. So room temperature, body temperature is a little higher than that. It's a pretty safe thing to say that my body temperature is around 300 Kelvin. And so if I put in 300 Kelvin, if I take this constant and divide it by my temperature, 300 Kelvin, to get a wavelength out, well, 3 times 10 to the 7 divided by 300 is about 1 times 10 to the 5, which you'll believe me when the slide says it. 1 times 10 to the 5, so 10 to the 5 angstroms, or about 10 microns, that's an infrared wavelength. And so my body temperature and your body temperature and the room temperature around us is all radiating light at infrared wavelengths. And that's why if you want to catch a burglar near your home, you install infrared cameras in your backyard. Because while you can't see the burglar at night, the infrared will pick up the burglar's body heat, and you'll be able to see him through the wavelengths in which he is naturally thermally glowing. And this is the same glow as stars. It's happening because of these random particle motions in all of our bodies. All right, so why do we see 2 humps on this picture here? So I've just talked about the thermal infrared emission. Go back. We'll get to that. That all of us emit. So this thermal peak here. What about this visible hump? So this is why we can actually see each other. And can we see each other because of the phenomenon that describes our t-shirts, or because we're all glowing in infrared? Why do we actually see each other sitting in these seats? Right, it's reflected light. And so if you were to take the whole spectrum of a human being, you would see this visible part, which would be the reflected light from some other source in this room. It's the room lights. If you were outside, it might be sunlight. And then as you went further away from the visible into the infrared, then you would see a second peak where that person's body temperature was causing them to emit in the infrared. So here's the picture of someone taken in the infrared. He's holding a lit match, so because it's hotter than he is, it's glowing very fiercely in the infrared. This red sort of represents high infrared temperatures. It's a false color picture. And so his body is mostly red, and then his sunglasses and apparently half of his tie are relatively cool. And so again, what that just showed was his infrared thermal emission, and when you were looking at him with your naked eye, you would have been seeing his reflected light, or the light reflecting off of him. So does anyone have any questions about Wien's law, or about the difference between seeing someone in reflected light and knowing that they're actually glowing in infrared light? Does anyone have questions they wanted to ask from before that I didn't get to? Okay, in the back. Yes. We'll talk about ages of stars later. I don't want to get into that so much. The question was, most of the stars we see mostly appear white, and do we infer from that that they're all about the same heat and age? We can infer from that at the very least that there's a range of temperatures that most stars are in that cause them to appear mostly white instead of red or blue. So maybe the stars that appear very red or very blue are sort of the more extreme cases. And ages of stars we'll definitely get to later in the course. Yeah, up here. Yes, Alex will have a lot of fun talking about how black holes actually do emit some radiation. And as it is, it just so happens that a black hole is as close as you can get to a black body. The fact that it emits almost no radiation whatsoever probably helps that cause, but I stand by my statement. All right. I feel like a politician up here. Okay, so this demo with different balls is just, again, to drive home the point that these colored balls that Alex was talking about last time are all about the same temperature, but as you can see, they're quite different colors. And so when you look at them with your eyes, you see different colors because they're reflecting and absorbing different wavelengths of light. But on the other hand, if we had an infrared camera and we were to look at all these balls in the infrared, because they're about the same temperature, all of the balls would look more or less the same. All right. So there's one more pattern that you guys might have noticed when I've been describing these spectrum, and I've been jammering on and on about how the location of this peak is somewhere different on this scale based on the object's temperature. But hopefully you guys have also noticed that the height of the peak is very different too, and that as we talk about hotter and hotter objects, we go from having low peaks to a higher peak to a higher peak and to a still higher peak. And again, because the vertical axis corresponds to brightness, that implies that hotter objects are brighter. And in fact, and you have to assume for this slide that we're talking about objects that are all the same size. So let's go ahead and assume that. You'll notice furthermore that not only is the peak for the hot objects brighter than the peak for the colder objects, but at every single wavelength on this graph, the hotter objects are brighter than the colder objects. And so if you have two objects of the same size but different temperature, it's actually true that the hotter object will beat out the colder object at every single wavelength you examine. And hopefully that doesn't strike you as being too counterintuitive. After all, the sun is much hotter than we are, and if I placed you at the distance of the sun, I wouldn't see you. I would still see the sun. So stars are much brighter than we are because they are much hotter than we are. Also because they're bigger, but even if we were as big as the sun, we wouldn't be as bright as it. Another good example of this is in the sun itself. You have sunspots, and so there are locations, these sunspots, that are actually darker than the rest of the sun around them, and that is because they're cooler. We'll learn about the physics behind sunspots a little bit later, but whatever that physics is, it causes sunspots to be cooler than the rest of the sun. And because these objects are cooler, and because photographs or our human eyes are actually very good at picking out contrasts in brightness, we see these sunspots as being darker because they're colder than the rest of the sun. I should have mentioned a while back, I know this is a really cool thing, so I'm sorry I forgot to mention it. Why do you think the sun, what do you think is the relationship between our eyesight, where we see visible light, and the fact that the star closest to us has its peak wavelength in the middle of the visible spectrum? Isn't that just the neatest coincidence you've ever thought of? Because it's not a coincidence. Life on Earth has evolved so that we naturally see best at the wavelengths that the nearest bright object, the sun, emits the most. So our eyes have evolved to adjust to the sun and the colors it emits at its temperature. If the sun was much cooler, I could almost promise you guys that we would have evolved to see red light and infrared light very, very well, and we probably wouldn't have a good concept of blue light. So back to this brightness versus temperature idea. Again, this is something that we can put a mathematical relationship to. The last one was Wien's law. This one is called the Stefan-Boltzmann law, and it's a relationship between the overall energy, so brightness and energy are very similar, produced by an object per unit area per time. So if you think about a star like the sun, or you think about a patch of your body, and you measured out a standard size, maybe a square centimeter, and ask over this square centimeter, how much energy does the sun release in light every second? Or how much energy am I glowing in infrared light over a patch of my body every second? We can relate that to, guess what, the object's temperature. And the proportionality constant is this sigma, the so-called Stefan-Boltzmann constant, which again, we like it because it's a constant. There is no circumstance where this number is different. It's always the same. And so, again, the energy per square centimeter per second is equal to sigma times temperature to the fourth power. I don't know if you guys have seen a law to the fourth power yet, but having something to the fourth power is very dramatic. What it essentially means is that if I change an object's temperature just a little bit, I'm going to make it a lot brighter, assuming I make it hotter, so that you get big changes in brightness from relatively small changes in temperature. And to illustrate that, we have a simple problem down here. We have a 6,000 Kelvin object that would be more like the sun. We have a 3,000 Kelvin object of about the same size. And we say, how much brighter per unit area per second is the sun compared to this 3,000 Kelvin object? And so to do this, we would take the ratio of this epsilon, the energy emitted per area per time, and that would be equal to the ratio of sigma times the temperature of one object to the fourth power over sigma times the temperature of the other object to the fourth power. Of course, sigma being a constant, it would just cancel out of the equation, and would be left with the two temperatures to the fourth power. And so this is a great example of a ratio problem. If you've been keeping up with the math in this class, we're trying to emphasize ratios. And so instead of going through all the nuisance of calculating 6,000 to the fourth power and getting some ridiculously big number, and then taking 3,000 to the fourth power and getting another ridiculously big number, and trying without a calculator to divide the ridiculously big numbers, all you have to do is realize that because you're taking the temperature to the fourth power in the general relationship, if you just take the ratio of the temperatures, 6,000 over 3,000 is 2, and you take that to the fourth power, then you quickly get an easy equation. 2 to the fourth power, which you should be able to figure out is equal to 16. So an object like the sun that is twice as hot actually is 16 times as bright in every patch of its surface area. That's pretty incredible. There's something to demonstrate this. We can go through quickly. And so again, I have an object set up like the sun. It's about the same radius as the sun. It's 1 solar luminosity right now, and it's about the sun's temperature. So like I was just saying, so this temperature right now is a little bit less than 6,000 Kelvin. If I raise the temperature to about 12,000 Kelvin, how much brighter would you expect it to get? I've made everyone go to sleep. I'm very sorry. 16. It would be about 16 times as bright. And so here we go. This scale is not too precise, but if I get it just below 1,200, there's the 16, 11,632. More or less twice the temperature, 16 times the luminosity. I wish this scale could go all the way up to 50,000 Kelvin, so you could see it get 10 times as hot. If I made it 10 times as hot, if I could do that, how much brighter would it be? So we take 10 to the fourth power times as bright. What is that? That's 10,000. And actually, in the universe, there are stars that are about 10 times as hot as the sun, and they, per surface area, are 10,000 times brighter than the sun. The sun is not close to the brightest thing that we have in the universe. Stars out there are much hotter and much brighter than the sun. And so to show that, I can crank it all the way up to 40,000, which isn't quite 10 times as much, and it gets up to 2,000 times as bright. So 40,000 isn't quite 10 times as much, and 2,000 is not 10,000 times as bright. And so I'll stop playing around and bring it back down to the temperature of the sun. All right. So we get that relationship. A good example that you might have seen, if any of you have been to a star party, is Albireo, the so-called Cal star. And so at the star parties, you've been looking at this blue-yellow binary star. So now, based on this lecture, all of you should be able to yell out, I don't care if you're asleep, yell in your sleep anyway, which one of these stars is hotter? Blue, the good star. The blue star, because it's good, because it's like the Bears. Go Bears! All right, so the blue star is clearly hotter. And so originally, based on what I'd said, wouldn't we expect the blue star to be much, much brighter than the yellow star then, because it's hotter? You would expect that, but you can see from this photograph that they're about the same brightness. Maybe the yellow star is even a little bit more bright than the blue star. And I should point out that in this image, the star sizes aren't what they look like in the image. The atmosphere tends to blur out starlight, so we're not seeing the star's actual sizes. We're seeing sort of a blurred out version from the atmosphere. So ignore how big the stars look, but still the point I'm making that the yellow star is about as bright is certainly true. And so something has to be going on. Otherwise it would go against everything I've said, that you can have a yellow object that's colder yet brighter than the blue object. And I've sort of already alluded to it. The thing that we're missing here is the object size. And so I've said that the Stefan-Boltzmann law that goes like to the 4 applies to an object's energy emitted per unit surface area. But if you have a huge object with a lot of surface area, naturally the entire object is going to appear brighter. So you can draw the conclusion, assuming these stars are about the same distance, which they are, knowing their different temperatures, but also knowing that the colder one appears brighter to you, that the colder star must in fact be much larger than the hotter star. Does that make sense to anyone? To everyone? Or anyone? All right, it makes sense. Great. And so going back to this demonstration I just did, I changed the temperature last time. If I change the radius, you should see the luminosity also increase with the radius. It also makes the star appear bigger. That's nice. And so if we go back, to fill in this finally, we had our original law that the energy emitted down here equals sigma times the temperature to the 4th. If we talk about luminosity, which was this epsilon, which is the energy emitted per square centimeter per second, multiply it by the surface area, to get the energy emitted by the entire object every second. We call that the luminosity of the object. We see that all we have to do is multiply the surface area times epsilon. So the surface area times sigma times c to the fourth, and sigma is a constant. If you plug in the formula for the surface area of a sphere, you get L equals 4 pi r squared sigma t to the fourth. This might look a little bit nasty, but remember when you're doing problems that 4 pi is certainly a constant, sigma is also a constant, and so all those numbers are going to cancel out, and the only things that matter when we're talking about how intrinsically bright, how luminous an object is the object size, its radius squared, and the object's temperature to the fourth power. So if we go back to my applet, you can hopefully predict if I keep the temperature the same and increase the radius by, say, a factor of 5, how much brighter, how much more luminous is this object going to become? So I'm increasing the radius by 5. Luminosity goes like the radius squared, and so it should be 25 times as luminous. So if I go up to 5, you can see that it's kind of cooperating. It's about 25 times as luminous, and I'm blaming the applet on this entirely. If you were doing your homework, you'd write 25, and you'd be right. I don't know why it's being picky between 25 and 26. Let's ignore it. And so, again, the bottom line is I can make an object brighter either by increasing its size, increasing its radius, or by increasing its temperature. And if I crank both up all the way, you get the biggest, brightest object that this Java applet can possibly conceive. But again, I want to point out that there are stars that are this big and this large and this bright in the universe. Stars are very, very hot, 40,000 Kelvin. Those same stars can be maybe 20 solar radii. And so the sun is a relatively wimpy star. Other stars can certainly exceed it in temperature and in overall brightness. And so if we go back to the CalStar one last time, we again conclude that because I've run out of things. Because this yellow star appears brighter to us and it's the same distance, it must be much larger. So everyone, enjoy your weekend. Watch the Bears destroy Colorado State at football. And I will be back on Monday to teach you guys about telescopes. Have a good weekend, everyone.